Hey guys, this is your master teacher Nabamita and today we are going to complete and start the chapter Classification of Elements and Periodic Properties. Now this chapter we can expect 2 to 3 questions in JEE Mains as well as in JEE Advanced, and guess what? This is the very basic of most of the inorganic chapters like coordination compounds, S block, P block and DNF block. So watch this session carefully because you can get a lot of marks into your pocket. So let's get set go.
All right. So here we are with one of my favorite chapters in inorganic chemistry, that is periodic properties, and absolutely in one shot. So let's quickly go ahead and let's take a look at what exactly is there in this chapter. And in this chapter, as we see, we have why do we need to classify elements? Because of course there are a lot many. Genesis of periodic elements, basically it will be a run through the history of periodic elements. Like obviously how the periodic table looks like today is not how it used to look like always, right? Yes, and obviously in the from the very initial days we did not have these many elements. As we are going on and on, as there are advancement in technologies that is happening, we can understand that we are discovering, we are inventing newer and newer elements, and hence we have to go through the history a little bit painful, but we can do it. Now we will be so basically what will happen, just like always, the very beginning, these are not going to be important for your JEE Mains or advanced, not at all for advanced definitely, but for boards it can be, for MSET it can be, okay. So modern periodic law and the present form of the periodic table, this is where we start with, we start revving up our engine. Nomenclature of elements, this is going to be very important. Electronic configuration of elements, remember, you have to remember it, and the periodic table, electronic configurations and types of elements, that is S, P, D and F block, and then we go through the blocks, that is S block, P block, D block and F block, but in short, because we also do have these chapters in both 11th as well as 12th standard, right? Then we read a little bit about the metals, non-metals and metalloids. Then we read about periodic trends and properties of elements, which is where the major most of the questions that you get from this chapter are actually from here, okay? Trends in physical properties, very important. Ionization enthalpy, very important. Electron gain enthalpy, very important. Electronegativity, very important. Periodic trends in chemical properties, that is oxidation state, anomalous properties of the second period element, and periodic trends and chemical reactivity. All of these are going to be super duper important for the chapter, okay. So moving on. First of all, what actually happened was, the year was 1800. Listen to the story and I promise you will get to know everything, okay. So the year was 1800 when there were only 31 elements. It was very easy. We did not have to classify because hey, 31 elements, we can easily figure out which element is what. We don't have to sort it out at all, right? Then came 1865 when the elements now became 63. Now we have to sort it out, right? And then by the year 2016, we have had 118 elements, right? Yes. So now that we see, out of 118 elements, my dear student, tell me something, do you know how easy it has become that you can only read about S block and P block and D and F block, right? That's it, done. 3 chapters, you are done with the whole periodic table. Now imagine if you had to, if you did not sort it out, if you had not classified all of these, and if you actually had to go through each and every elements, 118 chapters is what you would have to study. Would you like that? No, obviously not, right? Yes. And why classification is important is, as I always tell each and every student, is that understand this. Even in a very junior class, you have read that, classification allows us to understand the similarity in the properties, the dissimilarity in the properties, and that way we can learn about things way faster than we think we can, right? So now obviously when there are 118 elements, we understand that it is difficult to individually study the chemistry of each and elements, correct? Yeah. And as per the IUPAC, there are currently 2 million inorganic compounds and 18 million organic compounds. Tell me something, would you like to read about all of these million inorganic and million organic compounds? I'm kidding. Who am I kidding? I don't want to read that, yeah. Anyway, so an arrangement in which elements having similar properties were classified in tabular form, which led to the formation of periodic table, is what we are going to talk about, right? So the formulation of the periodic table, it provided a way for the study of chemistry in a much simpler way. Okay, all right. So first things first, it was when there were only 31 elements was when Doberanus triads had come. So how I used to remember is, I always remember it as Doberener, Doberman. That's how I remember it. So if you want, you can follow it. Otherwise, you can find something of your own, right? So what Doberener did was, he started grouping elements into three groups, right? 3 elements in one group, 3 elements in one group, 3 elements in one group. That's what he did, right? And he said that when there are 3 elements, right? When there are 3 elements, so if you take the first element and if you take the second element, add them, divide them by 2, you will get the second element's atomic number, which was true. For this, it hold good. It did hold good. For calcium and barium also, when he did this, he took the calcium, he took the atomic number of barium, and then he thought that he will find it for strontium, but that was not the case. There was a small deviation. There was a very chotu deviation. What is deviation? It was not following the exact path. It took a different path here, right? Then when we saw for chlorine, bromine and iodine, when you take chlorine and when you take iodine, and then when you try to find out bromine's atomic number, you could again see that there was a small deviation. So Doberener, obviously he was a pioneer at his age. He was someone who started for it, who started this trend of making something called as periodic table. But guess what? At this point, he had to agree that I surrender. I probably am not the best person to sort all of these things out, right? And that was just the beginning, right? That was just the beginning. If he probably would not have taken this first step, maybe we still wouldn't have reached to the periodic table, right? So when 3 elements having similar properties were arranged in an increasing order of their atomic mass, the atomic mass of the middle element is usually the mean of the atomic mass of the other 2 elements, right? That's what we see. So like I said, that it did not hold good for all the elements. At certain point, just when he started going to the heavier elements, he saw that it doesn't hold good. There was always some kind of deviation that he was finding, and that's when he had to surrender that, okay, all right, I agree, I have to take a step back. Probably I am not the best person to do this, right? So he left it. Now there was another person called as Newland's law of octaves. So he saw in the nature and he was like, oh, people sing, so sa, re, ga, ma, pa, dha, ni, sa. And that in Latin is do, re, mi, fa, sole, mi, ta, lati, something like that, right? Yeah. I think I just spoke about coffee now. Mi, latte. Yeah, anyway. So basically that happened, right? And then when he started, arranging the elements in an increasing order of their atomic number, he saw that the 1, 2, 3, 4, 5, 6, 7, he wrote it. And then he saw that the 8th element could repeat the properties of the first element. Yeah. So how you see lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? And after that, he again wrote sodium just below lithium. Now this was shaping up. This was shaping up our periodic table, right? Yes, so sa, re, ga, ma, pa, dha, ni, sa, just like that. Like I said, in Latin it was do, re, mi, fa, sol, la, ti, something like that. Obviously, Newland did not know about sa, re, ga, ma, pa, dha, ni, sa. Newland definitely knew about the Latin one. I do not know about it, yeah. So this happened, but obviously again after certain point, what happened is again it was not holding good. Again it did not work out. Yes. Again it worked only for the lighter elements. The moment you started going towards the heavier element after calcium, it failed. Yes. And the discovery of noble gases, when the noble gases came into the picture, that's when it took a wee deep dive. It just did not work out. Yes. And because it was not valid for heavier elements like oxygen, like iron, right? So it were all placed in the same group, although they had very different properties. Check it out. See, oxygen here, sulfur here. Chalo, oxygen and sulfur are still fine, right? Yes. So it did not hold good. It just did not work out. And once again, Newland also said that fine, I agree to it. I'm not gonna do anything. Now there was another person. Now this person, according to me, is the one who actually shaped things up for real. Okay, for real he did that. So what he did was Lothar Meyer. What Lothar Meyer did was he took atomic volume and he plotted it against atomic mass. Atomic volume, mass and volume. When he plotted it, my dear students, please check it out. This graph is very interesting. Okay, this graph is very interesting. What he saw was helium, yes, okay. Then you see sodium, yes, potassium, all right, rubidium, cool, checking it out, potassium, rubidium, sodium, yes, okay. Now see, one second, huh, fluorine, okay, now with a different color I am going to put it, yes. Now check it out here, fluorine, chlorine, okay. Then again you will see bromine, yeah. Now what he saw was, there was another thing that he saw, okay, there was another thing that he saw, lithium, magnesium, calcium and strontium, right, okay, these are the things that he saw. So what actually he saw that the alkali earth metals, what did I say, the alkali earth metals, right, the first group elements, alkali earth metals, alkali metals, no, alkali metals, right, the first group elements, that is sodium, potassium, rubidium, they are all found at the peak of the graph. Noticing it? Yes. Then he saw that the halogens, fluorine, chlorine, bromine, when the graph was taking an ascent, when the graph was going up, at that point you will find them. That's where you will find them. And just above them or just around that, you will see that noble gases are also there. Neon, argon and krypton. He figured that out. And then he saw when the graph was descending is where you could find the group 2 elements. Magnesium, calcium, strontium. See? And then at this part, okay, at the bottom part, if you see, at the bottom part, see, here manganese, cobalt, nickel, zinc, gallium, right? At the bottom part, right here, you could find all the metals, or we can say the D block elements mostly. That's what he found out. So this was exceptionally great, right? So basically what I have just told you is what I am writing it down here. Alkali metals are at the peak of the curve. Alkaline earth metals are at the descending part. So yes, group 2 alkaline earth metals are at the descending part of the curve. Halogens are at the ascending part of the curve, and most of the transition metals are lying in the broad minimas, right? That's what he said, okay? That's what he said. Now obviously Lothar Meyer did a great job, yes, but there were many other physical properties of the elements which also change in a periodic manner. He saw that melting point, boiling point, density, thermal expansion coefficient, these also do change on a periodic manner. And based on this properties or based on this observation, you know what he proposed? He said that the physical properties of elements are actually the periodic functions of their atomic weights, that means atomic mass. He spoke about atomic mass. He said that the physical properties of elements are periodic functions of their atomic mass. Atomic mass he spoke about. That's where he went wrong. And this is where Mendeleev took his idea from. No doubt Mendeleev is the father of the periodic table, right? The acha of the periodic table, no doubt about it. But from where did he get the idea? He got the idea from right here. Atomic weights, atomic mass. Mendeleev changed it a little bit and he figured it out that it was not atomic mass, but it's actually atomic number, right? So the physical and chemical properties of an element are periodic functions of their atomic masses. Yes, right? So Mendeleev took the same idea and he said the same thing, right? So in Mendeleev's periodic table, at that point of time, there were 7 rows. You understand what is row? This, horizon, that's rows, okay? And columns are this, vertical columns, top to bottom is column, okay? So there were 7 rows and there were 9 columns and they were named as group. At that point of time, we did not have group 1 to group 18, but we had something about group 1 to 7, and all of these 7 had A, B, A, B, A, B. Yeah. Then there was group 8. Group 8 had A, B, C, and then there was a 0 group as well. Okay. There was a 0 group as well. There was a 0 group, there was group 1A, group 1, group 1A, group 1B, group 2A, group 2B, group 3A, 3B, like that it was there, okay, alright. So basically it looked like this, see 1AB, 2AB, 3AB, 4AB, 5AB, like that he had written, okay. And he could also see that at that point of time he spoke somewhat about oxide and hydrides also, right. So in the group 1 he had kept hydrogen, lithium, sodium, potassium, rubidium, cesium, pretty much like how our periodic table looks like right now. Then you see in group 7, 6, 7, he kept fluorine, chlorine, manganese, technetium. That was somewhat wrong. Although in today's group 17, we do have fluorine, chlorine and all of that, right? Yes. So what Mendeleev did was, pretty much everything was great. Everything almost looks great. But there was one thing that he has done is this, do you see? 3 elements in the same column he had kept. 3 elements he had kept. So merits of Mendeleev, what were the advantages that we could see from Mendeleev's periodic table is that if the elements are arranged in the order of their atomic weights, increasing atomic weights, you will see that after the regular interval of elements, similar properties are repeated. Similar properties do repeat. And the table is divided into 9 vertical columns and 7 horizontal rows. Correct? Great. We have just spoken about it. What he did was he placed elements having similar nature in the same vertical column or group with respect to atomic weight. He took atomic weight as the main factor, and then he started just grouping them into different columns, right? And at some places, the order of atomic work, this is something that he did great, okay. So at some places what he did was the order of atomic weight was changed a little bit in order to justify the physical and chemical nature of elements. And in some places, the best part of Mendeleev's periodic table was that he left some places empty and he said that today it's not discovered, but wait for it. There will be elements that will be discovered in some time. And that was, lo and behold, it was true. Isn't that interesting? It is interesting, right? Yes, he left places and he said that you don't believe me, you wait and watch, there will be newer elements that will be, discovered. And it was great. We did discover newer elements, and which had exactly the same place as Mendeleev predicted. Yes, that was when, our mind was blown away and we fell in love and we started calling him the father of periodic table, right? Yes, so like I said that he left some gap. For example, there was Eka aluminium, yes, there was something called as Eka, there was something called as Eka silicon that he predicted. Eka aluminium was predicted, but later on we found that there was gallium was found. See, he said that the atomic mass of this Eka aluminium, Eka is from Sanskrit, right? So if there is aluminium, he said that there will be Eka aluminium, like ek or aluminium, like another aluminium, right? That's what he said. In Sanskrit, he said that Eka aluminium, he predicted that the atomic mass will be around 68. And then when gallium was discovered, right, we actually figured that, ooh, gallium has an atomic mass of 70. Just the difference of 2. Come on, let's give it to him, right? Let's give it to him. That's pretty accurate, correct? Okay. Then he said that Eka silicon will come. There will be an element which will be called as Eka silicon, and he said that the atomic mass will be 72. And when we found germanium, when we discovered germanium, we got to know that wow, the atomic mass is just 0.6 difference, 72.6. Lo and behold, what an amazing guy, right? He also spoke about the density. He said Eka aluminium will have 5.9, and yes, gallium had a density of 5.94. Really, it's kind of crazy that he did that, right? Eka silicon was 5.5, that's what he predicted, and guess what, germanium had 5.36. Yes. Then he said that the melting point of Eka aluminium will be low, and yes, gallium melts in your hand, very low melting point. He said that Eka silicon will have high melting point, and look at it, germanium has 1231 melting point in Kelvin. Formula of oxide will be EtO3, and yes, gallium has Ga2O3. He said that Eka silicon will have EO2, germanium has GeO2, right? Then formula of chloride will be ECl3, and yes, gallium has GaCl3. Eka silicon, he said ECl4, and yes, germanium had GeCl4. You get it? You get it? Yeah. There is uncanny resemblance to what he said. I mean, it's almost like he's a magician, right? He's a magician. And then, like I said, the determination and correction of the doubtful atomic weights, right? So, atomic weight, see, for beryllium, earlier we used to think that it was 13.5 and valency was 3, okay? But that's not the case. Corrected atomic weight came out to be 9.01 and valency was actually only 2. Beryllium, group 2, yeah? Beta mange car scooter, like, yes, beryllium, magnesium, yes, beryllium is in group 2. Group 2 has a valency of 2 only, right? 1s2, 2s2, correct, that's it, yeah, that's what he said. Now, obviously, it wasn't like there were no demerits. There were demerits, which is why we have the modern periodic table in the picture, right? So, in Mendeleev's periodic table, there were certain demerits. What was it? That the position of hydrogen element was not justified. By the way, if you are thinking, the position of hydrogen element is actually not even justified today. If you can figure it out, guess what? You are going to get a Nobel Prize. I'll be very happy. Do let me know that, ma'am, I got a Nobel Prize. And I can brag about it that one of my students got a Nobel Prize. Yes. So, even in the modern periodic table, the position of hydrogen element is still not justified. There were no separate positions given to isotopes. Why are we talking about this? I know for right now in today's world, isotopes not getting a different, a different cell makes sense. But at that point of time, Mendeleev's periodic table was actually based on atomic weight. We're talking about atomic mass, and isotopes have different atomic mass, right? That's why we're talking about it. So, he could not create different cells for. So, the order of increasing atomic weights were not even strictly followed in the arrangement of elements, right, in the periodic table. What he did was, cobalt atomic weight 58.9 was placed before I-127, yes, before I-127. I think that makes sense. That does make sense. 127 is supposed to be later, right? And argon 39.9 was placed before potassium 39. So, that was basically deviating from his own laws. He prepared the law, right, and he said that according to atomic weight we will arrange it, but then we saw that that was not the case. Now, there was no explanation for the periodicity of the element. There was no explanation. Like, you could see that it was kind of haphazard, right? At certain point it was haphazard. And also there were no separate place for noble gases or inert gases. So, it failed. It failed. And then comes the true visionary, that is Sir Henry Moseley. What Henry Moseley did was, now this time he said that, you know what, let's change our thought process a little bit. Why talk about atomic weight again and again? Let's do one thing. Yes, let's do one thing. What he did was, he watched the characteristic of X-ray spectra of the elements, and then he plotted a graph between the root of frequency with versus atomic number. Okay, what did he do? He plotted a graph of root of frequency versus the atomic number, and that's when, boom, he saw that, oops, all these while that we were talking about atomic weight, it was not actually atomic weight, but it was actually atomic number. It was actually atomic number. Yes, it was actually atomic number. So, he said that the properties of elements are the periodic function of their atomic number. The properties of the elements that you see, it is actually what? It is actually a periodic function of the atomic number. Okay. Alright, so what are the key points of modern periodic table that Moseley came up with? The classification of element was based on atomic number, which is a more fundamental property. Understand this, atomic weight is not a very fundamental property, but atomic number is very basic fundamental property, because every element is going to have a different atomic number. Atomic mass can still be same like isotopes, but atomic number has to be different, right? And then he said that, so the reason that Mendeleev did not give separate spots for isotopes, now it makes sense, because isotopes have essentially the same atomic number, they just have different atomic mass. So it makes sense that you did not give a separate cell for isotopes, right? Then he said that it explains the periodicity of the properties of the elements and relates them to their electronic configuration. Now he also started looking at the electronic configuration, and he said that the periodicity of the properties of the elements can actually be related to the periodic properties, and we actually be related to the electronic configuration. And yes, if you look at all the group 1 elements, you will see that they always end with 1s1, 2s1, 3s1, 4s1, 5s1, right? It never changes, it's always S1, correct? Then he spoke about the lanthanides and the actinides. They are placed separately at the bottom of the periodic table, because if you bring them in the periodic table, in the main periodic table, they just mess up with the beautifulness, the beauty of the periodic table, how it looks like, okay? So this is the actual periodic table that we have right now. And see, you must have noticed that in certain places what they do is they keep the hydrogen here. Certain places they keep hydrogen here, because like I said, even the modern periodic table does not have a place for hydrogen. And that is why when we are studying about S block, we never study about hydrogen. Hydrogen is a separate chapter, my dear students, right? Because hydrogen has its own properties, does not really share it with anyone else, because it is not an S block, it's not a P block. It does share some of the properties with the group 17 elements, this fluorine, chlorine and all of this, and it does share some of the properties. It has similarities with the group 1 elements, and we still do not know where should we place it, but because the atomic number is 1, so we just say that, hey, let's start from here, right? Okay. Now if you look at it, so these are, as you can see, now in the modern periodic table, this used to be 1A in Mendeleev's periodic table, but right now we just call it group 1. This used to be group 2A in Mendeleev's periodic table, but now we just call it group 2. Yes. And then if you see that there was also group 13, it was called as 13A. Now we call it group 13. 14 was 4A. 15 was 5A, 16 was 6A, 17 was 7A, and 18 was 8A. And then you see that 3B had scandium, yttrium and lanthanoids and actinoids. 4B had titanium, zirconium, hafnium and rutherfordium. Yes, 5B had vanadium, niobium, tantalum and what was it? I forgot the name. Then it was chromium, molybdenum, tungsten and all of that, right, in the F block. F block, when we do it, we will study about the names. Their names are a little weird. So we will learn about it, don't worry. So basically this is your whole periodic table, and in the modern periodic table now you have 18 groups and you have 1, 2, 3, 4, 5, 6, 7. You have 7 periods and 18 groups, okay? Alright, got it? So what do we have? The vertical columns, the top to bottom, they are known as the groups. The horizontal rows, they are known as the periods. So there are total number of 7 periods, there are total number of 18 groups, and the elements that are placed in the periods are based on the shells in their atoms, okay, based on the shells. So for example, if you have an element in the S block, that means it has S shell in the outermost. If they are placed in the P block, that means their electrons go into the P shell, okay. If they are in the D block, that means their elements go into the D shell, right? You got it? I think it's very simple, very easy, right? Okay, we got it, understood. Now, so the leftmost group, this is known as what? Alkali metals. Why? Because they, whenever they form hydroxide, they form very strong alkali hydroxide, right? That's why we call them as alkali metal group. The second group is known as alkaline earth metals, that is beryllium, magnesium, calcium, all of that, they are known as alkaline earth metals. Group 3 to group 12, We will be studying about it in D block elements, and they are called as transition elements, okay. Why do we call them transition elements, by the way? Have you figured? Because see, if this is S block, I'm jumping to S block very fast. If this is S block and if this is P block, right? So when you look at the properties of S block and when you look at the properties of P block, what happens is in between the D block, they transition the properties of S into P. Basically from S block to P block, when you are going from S block to P block, you notice that these D block elements, they have the properties that are transitioning into the P block. And that's why we call them transition elements. I hope you got it, right? Yes, okay. Then the group 17 is known as halogen family. What is it? Halogen family, that is fluorine, chlorine, bromine, iodine, astatine. Those are all halogen family, right? And then group 18 is noble gas group, and it is also called, it was called as the zero group. However, we don't call it zero group anymore. Nowadays we call it group 18. Group 18 is your noble gases, neon, argon, helium, all of that, krypton, xenon, radon, right? These are all your group 18 elements. Great. So now, if you want to know the features of the modern periodic table, just take a look at it. Yes, the first period is n is equal to 1. Orbits that are filled up in the first period is 1s. The number of elements in the period is only 2. Hydrogen and helium are the only 2 elements. Atomic number starts from hydrogen and it ends at helium. This is a very short period. Then we come to second period where n is equal to 2 and the orbits that are being filled up here is 2s and 2p. So the number of elements in the period is, take a look at it. Take a look at it. May I tell you something? Tell me something, 2s and 2p. How do you write the electronic configuration? You write it as 2s2 and 2p6 it goes, right? So 6 plus 2 is 8. Is 8. So the number of elements in the periodic table are 8 here. It starts from lithium. Lithium's atomic number is 3 and then it ends at neon. Neon has a atomic number of 10. What is this? This is a short period, right? Moving on to third, n is equal to 3. Orbits that are being filled up is 3s and 3p, where we again see that the number of elements in here is also 8 and it starts from sodium 11, ends at argon 18, and this is also a very short period. Then we come to fourth period. Now in the fourth period, we see that the orbits that are being filled up are 4s, 3d, 4p. And this time, because 3d orbitals have 5 rooms and in the 5 rooms you can fill 10 electrons, so it is basically 2 plus 10 plus 6 is equal to 18. This is equal to 18. Starts from potassium 19 and ends at krypton 36. It is a long period. Fifth period, you have 5s, 4d and 5p. Once again, when you do it, you get to see that this is 18. Rubidium, it starts from 37 and xenon 54 is where it ends. It is also a long period. Now we come to the sixth period where we have 6s, 4f, 5d, 6p. Now 4f can fill 14 electrons. So look at it. 2 plus 14 plus 10 plus 6 is equal to 32. Right? So it starts from cesium 55, runs till radon 86. This is a very long period because there are 32 elements in this group. Then we come to 7th where 7s, 5f, 6d and 7p, 2 plus 14 plus 10 plus 6 is equal to 32. Starts from francium 87 and goes to oganesson, Og is the last element. Og is the last element. Isn't it amazing? It is amazing to know, right? Og is the last element in the periodic table. It's called as oganesson. 118th element is your very long period. Okay, all right. By the way, there was also a controversy related to periodic table. So what happened was, there was this point of time when we saw something called as Rutherfordium here, right? Rutherfordium, yes. We have something called as Rutherfordium. So when Rutherfordium was actually discovered, right, and there was at the same point of time, there was another country which was also which also discovered Rutherfordium. So the name of the Rutherfordium was given by the Americans, and then there was this other country, they also wanted to name it as their own scientist name. They were like, no, our scientist discovered, we want our scientist name, right? So both of them, now the Americans and this country, they started fighting. I forgot the name of the country, but the story is interesting, so let me tell you. So both of them started fighting. They're like, no, we want our name. No, we want our name. No, we want our name. They kept fighting. And that's when IUPAC, the International Union of Pure and Applied Chemistry, they stepped in. And they said, hey, stop fighting. Yes. And what did they do? Do you think that this took the side of the Americans, or do you think that this took the side of the other country? They did not take anybody's side, and they said, I am going to tell you how to name your elements. You can't do this, okay? All of these things that you are doing, it's done, over, done and dusted. Forget about it. Now we are going to name the elements in a certain manner, and I'm going to tell you about it. So it was IUPAC who came up with the nomenclature which we are going to study now, right? But before that, you understand, this is your S block, this is your P block, this is your D block, this is your F block. The S and the P block are the main groups. They are called as, what was that word? You know what you do when you are, representative, yes, representative blocks. The S and the P block are called as representative blocks. It was so close in my mind. Yes, they are called as representative blocks because they are the main blocks of the periodic table. D block is called as the transition elements. Yes, the transition block. And because inside the D block, right, at this place, right, 57 to 71 is you have lanthanides and 89 to 103 is your actinoids. So these ones are called as inner transition elements. What do we call it? We call them as inner transition elements. Got it? So these are the 4 different blocks that we have. Now let's come to nomenclature. So this is why I told you the story, right? So Rutherfordium, regarding this element, people started fighting, and IUPAC was like, no dude, you can't do that. I am not gonna take another world war just because you want to name the elements how you want, right? So I'm gonna tell you how you have to write, and IUPAC is a very big organization of chemistry, right? So when they stepped in, it was like, whoa, baap aa gaya, and everybody was like, yeah, let's stop it, let's not do that, right? So what he said was, after the atomic number 100, right, any element with atomic number 100, how you are going to name them is, you're going to take the digit root. You're going to take the root of the digit. Yes. For example, if it is 0, then you take the word root as nil. If it is 1, then it is un. If it is 2, it is bi. If it is 3, it is tri. If it is 4, quad. If it is 5, pent. If it is 6, hex. 7, sept. 8, oct. 9, n. N. E, n, n. N. Okay. So the successive roots are put together and then you end it with iam. For example, if I have something called as 115. If I have an element with 115, how am I going to name it? I'm going to name it as, check it out. What is un? What is 1? 1 is un, right? So I'm going to write it as un. Then there is another one, so I'm going to again write un. And then there is 5, so I'm going to write pentium. Okay, alright. Same like that, now if I have, let's say 119, let's just say that there is another element that we have discovered. So how we are going to do it? We're going to write it as ennium. Alright, yes. Now if I say that there is another element that has been discovered and let's just say that it is 127, the atomic number of the element is 127, how am I going to write it? I am going to write it as unbiseptium. Now believe it or not, from here JEE 2020, fresh question everybody. Just 2 years back, JEE had asked you a question like this. Can you believe it? Not even kidding. Check it out. I know some of you actually do that. Some of you are like, ma'am, you're just giving us hopes. No, they actually did. 4 marks, free ka. Look at this. The atomic number of anium. So un is 1, nil is 0, anium is 101. That's it. This could get you 4 marks, guys. This could get you 4 marks. Yeah. All right. Chalo, great, amazing. So now you have understood this, okay? Now we are moving on towards the bigger part of the lesson, okay? But before that, I'm going to drink some water. You should too. So I'm recording it at very late night right now, and it is, I think, about 2 o'clock. And I'm here in the office. Yeah, crazy, right? But anyway, you know, this is called dedication. You see, we delayed the launch of this series a little too much, and I just thought that I cannot do this. I have to just, you know, take the plunge and record as much as possible. So I'm going to record till the time I actually drop down on the floor. Really. But anyway, chalo, moving on. Now we're going to talk about screening effect. Once again, I'm going to tell you a story. So there are too many texts here. Don't focus on this. Listen to my story. You will be able to understand it. So what is the screening effect or the shielding effect, right? Once I was actually traveling in an Uber, right? I was traveling in an Uber, and in Bangalore there is this place called Silk Board. Silk Board always has heavy traffic. And I think just before Silk Road, you can also get up on a flyover, right? You can also get up on a flyover. So at that time I used to work in a different office. I think it was just after my graduation, long time ago. And I was around, I think I must be 22, 23 years old, very young, right? As I was working at that time in Tata Consultancy. Yes, I was in TCS. So I was going by the, it was not Uber actually, it was office cab. Anyway, coming to the point. So I was traveling in it, and then suddenly we saw that there was a huge group of people who were all standing in the flyover and they were looking at something, right? Now, A, we were getting late for office, so we did not want to get down. B, it was also a flyover, so we did not want to get down. C, there were too many people, so we thought that we probably won't be able to watch anything, so we just moved on. But we wanted to find out what actually was happening, right? Now we did this, we wanted to look at it like what really happened, but we couldn't see anything, like nothing at all, right? Now what happened is we asked some guy like, excuse me sir, what is there? He said that tiger is there. So we were like, okay. Then we asked ki tiger hai or is it lion? He said ki huh. He said huh. So I'm like, tiger is also there, lion is also there. He's like, huh. It's like, okay, great. Silk Board, middle of the traffic. How can lion and tiger both be there? It's not the zoo. So now understand my point, what I'm trying to say. The moral of the story was not the fact that lion and tiger both cannot be there, but the moral of the story was because there were so many people. The person who I asked that, Bhaiya, what is happening there? Excuse me, sir, what is happening there? He also probably could not see anything because there were so many people and he was standing. He also couldn't see anything. Do you know why? Because there were people before him who were blocking his vision. But the people behind him, they were not doing anything, right? They were not doing anything to his vision. But the people who were before him, the people who were just ahead of him, they were blocking his vision. Use the same analogy in an atom. In an atom, use the same analogy. Let's say that this is my nucleus. Okay, this is my nucleus. The yellow color part is my nucleus. Correct, everybody. Now, what if I start making some, this is my shell. This is also my another shell. This is also my another shell. Now, let's say that I have an electron right here. But I will obviously have electron here, I will obviously have electron here, I will also obviously have electron here and here and here, and I will have electron here and I will have electron here, right? Yes? So now this electron is supposed to be pulled in by the nucleus, centripetal force and structure of atom, if you remember. The nucleus is supposed to pull the electron closer to it, correct? But there is another negative charge here. Negative, like charges repel like charges. Unlike charges, they attract each other. So although the nucleus is trying to pull this electron towards it and keep the atom not messed up but stable, what is happening is this electron is saying that, Poda, I won't let you come here. Poda. So this electron is repelling this electron. Getting my point? And this fact that this electron is getting blocked by these electrons, the outermost electron is getting blocked by the inner orbital electrons, is called as nothing but screening or shielding effect. Just like how that man could not see what actually was happening, and he told me that lion and tiger both are there in the middle of the road in Silk Board, where there is, Silk Board has international level memes, guys. It's that, you know, it has that much of traffic, right? So you understand that how can you have lion and tiger? What he saw, he doesn't know. He just said some story about it. The same thing is happening here. The nucleus cannot see this electron clearly. So the nucleus thinks that, nah, I am exerting my pressure, I am exerting my force, yeah. I have to exert electrostatic force, I am exerting it, but the nucleus still doesn't know that it is not able to reach here because these electrons, they are like, poda, we want it. And guess what? Even this electron is facing some amount of repulsion by this electron. Are you getting my point? Yes? By this electrons, the first orbital electrons are exerting some repulsion on this electron. So in a multi-electronic system, it cannot have a single electron. In a multi-electronic system, the electrons are attracted towards the nucleus, but they are also repelled by each other. The other electrons that are present in the inner orbitals, they repel them. So the force of attraction between the nucleus and the shell electron is somewhat decreased now. So let's just say that the nucleus was exerting a force of, let's say, 10 Newton, okay? Just example, obviously it cannot exert a force of 10 Newton, right? Let's just say that if it is exerting a force of 10 Newton, right? So the nucleus is thinking that 10 Newton will reach here only. 10 Newton will reach this electron. But that's not happening. Actually, what is happening is slowly and steadily, because of all the repulsion and everything, only 6 Newton is being, is being catered to this electron. And this fact that 10 Newton was exerted and 6 Newton reached, okay. So this is called as the effective nuclear charge. That means the nuclear charge that actually is affecting the electron. Not the nuclear charge that the nucleus was exerting. We are talking about the effective nuclear charge. The force after the force of attraction and the repulsion, the force that the electron, the outermost electron is experiencing is called as the effective nuclear charge. And that we give it as Z star is equal to Z minus sigma. Now what is sigma, you are going to ask me, right? What is sigma? Sigma is the shielding constant or screening constant, okay? What is sigma? Sigma is the shielding constant or screening constant. Now you are going to ask me, so what is it? So this we can calculate it with a rule called as Slater's rule. So there was this chemist called Slater, and Slater said that an electron present in shells higher than concerned electron contribute to 0, contribute to sigma 0. Again, remember that incident, that story I told you? So I was behind that fellow, that man who told me that there is lion and tiger both on the road. I was behind him. Did I contribute anything towards that gossip he told me? He told me a piece of gossip. He said that lion and tiger both are found on the middle of the road in Silk Board where there is huge amount of traffic, right? That was the gossip he gave me. But did I participate? Did I contribute anything towards it? I was behind him. I did not. I only asked him, like, bro, what's happening? And he told me a piece of gossip, right? Yeah. Now, whoever was with him, they also did not know. But they were like, it must be lion and tiger. But how can it be lion and tiger? They were all probably discussing. So now understand, okay, now understand. Let's check it out. This is my nucleus. This is my nucleus, right? This is my nucleus. Now, I have one shell here, my second shell here, third shell here, fourth shell here, fifth shell here, okay? Now, I'm going to draw electrons. Here is one electron, here is one electron. Now let's just say that I want to find out what is the Z effective charge on this one, this electron, this blue electron. What is the Z effective charge? Now this shell and this shell are outside. Will they contribute? No. So 0 plus. Now how many electrons are there in this particular shell? There are 1, 2, 3, 4, 5. 5 are there. So 5 electrons that are present in this particular shell, how much will they contribute? They will contribute 0.35. So I am going to multiply it with 0.35. Okay, that's it, done. Then I have, see, 1, 2, 3, 4. Next one has 4. So 4 into, now next one, n minus 1 will contribute 0.85. See, 0.85 plus the last one, this one will contribute 1, 2, there are how? 1, 2, 2 electrons. So it will have 2 into 1. It will contribute 1 to sigma. So now if you calculate 5 into 0.35, 5 5s are 25, 2 5 3s are 15, 16, 17. So, and then 5 zeros are 0. So it will be after 2 decimal 1.75, right? Yes. Then again 4.85 if you do. So just do it, calculate all of these, you will get a result, and that will be your Z effective. That will be your sigma. First of all, you will find sigma like that. Then you know the atomic number. Then you know the then you can calculate the nuclear charge also. Let's do a calculation. Let's do a question. Okay. Calculate sigma and Z effective for 4s electron in Mn Z is equal to 25. So how you are going to solve it is, let me tell you this. It's very easy. Okay. So it's given to you that Mn is equal to 25. The first thing that you will do is write down the electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So 10, 10, 20, 4s2, then 3d, 4s2, then let's write 3d, 5. Okay. Actually, you know what? Let's write it like this, not like this. Okay. Now see, in this case you only have one electron. Yes. Sorry, you have 2 electrons. 2. In this you have 8. In this case, how many do you have? You have 2, 5, 6, 11, 12, 13. You have 13, and here you have only 2. Correct? Now Z effective for 4s electron, that means this electron. So in this case, what do we have to do? Let's start from here. So that means that 2 into 0.35, okay, plus 13 into 0.85, right? That's the formula, isn't it? Yes. Okay. All right. Then after that 8 into 1 and then 2 into 1. So calculate all of this. What is the result that you are getting? First calculate this. Or let's also do it together. Chalo. So 2 into 0.35 plus 13 into 0.85 plus 8 into 1. I am so sorry, calculator made a mistake. 21.75. What is it? 21.75. So this is equal to sigma. Now what do I have to find out? I have to find out Z effective is equal to Z minus sigma. So 25 minus 21.75 is equal to, as you do it, I think it will be around, you know, I can't even do this. It's going to be 3.25. So that's your answer. Okay. That is your answer. Got it? Clear? Alright, moving on from here. Yes, so 3.25 is what we found, but here if you see the Z effect experienced by 4s 1 electron will be around 3.60. So the only difference that we have done is I have calculated is at 0.31 number of remaining electrons, so it will be 0.35 into 1 instead of 2 here. Instead of 2 here, what you can do is you can take 1. So when you take 1, then the difference will change, okay? That's what you have to do. Now, what are the factors that affect this shielding effect? The shielding effect actually depends on the number of inner shell electrons. The more number of inner shell electrons you have, the more will be the repulsion experienced by the outermost electrons. Shape of the orbital. Yes, the s orbitals, because they are spherical, they experience a lot more shielding effect than anybody else. The shielding effect in s orbital is the highest, then comes p, then comes d, and f has the poorest shielding effect. It does not even matter. I mean, their shielding effect is almost equivalent to nil, okay? They have very, very, very less shielding effect, okay? Alright. Now, let's take a look at atomic radii. As I was saying, atomic radius, as the name suggests, is basically the radius of the atom. Nothing different, correct? Yes. But tell me something, do you really think that you can take the radius of an isolated atom? Just one single atom. Will you be able to do it? Not possible, guys. Not at all possible. And let me tell you why. Yes. Because first of all, it's very difficult to make an isolated atom. Yes, to break the bonds and make it as an isolated atom, and then to measure the radius is just going to be impossible. Which is why what we do is we take two atoms together, and then what we do is measure the nucleus, the distance from one nucleus to the second nucleus, and then just divide it by 2, you get the radius of it, okay? Yes, so basically if I calculate from here to here, then this becomes my diameter, right? This becomes my diameter ideally. So just divide it by 2, it will give me the radius, correct? Yes. So the isolation of single atom is very difficult, which is why we cannot do it. Secondly, there is no well-defined boundary for the atom. The probability of finding the electron is 0 only at infinity. We still do have chances of finding an electron, right? So the boundary of atom is also not clear. So how will we find out the difference? But if we take two atoms together, then we can figure out the internuclear distance and then just half it, you get the radius, okay? Alright, so this is the more accurate way of finding an atomic radius. But is that the only thing? No. Now atomic radius has three different types, my dear students. There is covalent radius, there is metallic radius, and there is van der Waal radius, okay? Alright, so how do we figure out covalent radius? What is covalent radius? This is basically the half of the internuclear distance between two nuclei of atoms that are bonded by a single covalent bond. If there is just one single covalent bond, and we are talking about a homonuclear membrane, that means both of them are same, okay? Both of them are absolutely same. If you have a homonuclear molecule, then what you can do is the distance between AA divided by 2 will give you radius, okay? As it is, great, amazing. But now if you have a heteronuclear molecule, bole to this is a different kind of an atom and this is a different kind of an atom. Now if I do DAB divided by 2, will I get an accurate answer? No, I won't. And this is why there is a formula called Schumacher and Stevenson formula, where we said that d of AB is equal to radius of A plus radius of B minus 0.09 delta x. What is this delta x? This delta x is basically the electronegativity difference. What is it? Electronegativity difference of the atoms. Okay, what is it? Electronegativity difference of the atoms. Got it? Yes. Now this is in angstrom. This, if you want it in angstrom. Okay, all right. Yes, if you want it in if you want it in not in angstrom, if you want it in something else, then you will have to just keep it as minus 9. Okay, you will have to keep it as 9. Now this was not actually correct. This was not actually correct. So Stevenson and Schumacher, they gave a formula where you can write that the distance between A and B is equal to radius of A plus radius of B minus 0.09 delta x. What is this delta x? This delta x is basically the electronegativity difference. Okay, what is it? The electronegativity difference. All right. Okay, great. Okay. Now this is when you want to find it out in angstrom. If you want to find it out in picometer, then what you are going to do is, instead of writing minus 0.09, you are just going to write minus 9 delta x. That will be in picometer. Okay. Now this formula was actually modified, and a corrected version of it was given by someone called as Porterfield. Okay, someone called as Porterfield. Right. What did Porterfield say? Porterfield almost kept things same, but he said that RA plus RB minus 0.07 delta x. That's what he said. Okay. So this is the Porterfield formula. This was later, after correcting, he gave this. Let's do a question here. Given that covalent radius of fluorine, En is equal to, electronegativity is given to you, so 4, and chlorine is En is equal to 3. So 71 picometer and 99 picometer are the two radiuses that you have. Okay. Find the bond length of FCl molecule. Let's check it out. So basically what we have to do is, Ra is given. Yes, Ra is given. So let's say that Ra is equal to 71 picometer, Rb is equal to 99 picometer, right? Yes, and En of fluorine is equal to 4 and En of chlorine is equal to 3, right? So basically what we are going to write is 71 plus 99, as we can see here, see 79 plus 99 minus 9 this time, because both of them are in picometer, right? 9, and then what we are going to do is 4 minus 3, isn't it? So 71 plus 99, it will be 1, 9, 10, 1, then 9, 1, 10, 117. So 170 minus 9, and 4 minus 3 is definitely 1, right? So 170 minus 9 is equal to 161. So that means option D is the correct answer. Yes, option D is the correct answer. Very simple, very easy, right? Great, amazing. Now because it was in picometer, what we did was, we just did minus 9. Okay, if it was in angstrom, if it was given in angstrom, then we would have done minus 0.09. Okay. Now moving on, what is metallic radius, guys? What is metallic radius? Metallic radius obviously is measured between metals, isn't it? It is defined as half of the internuclear distance between the nucleus of the two atoms in a metallic crystal. Okay, all right. So if you have a metallic crystals, basically what you are doing is, again, this nucleus and this nucleus, find the distance and then just divide it by 2, you will get the metallic radius. Metallic radius is very simple, right? But now we come to van der Waals radius. Okay, here what happens is, you cannot measure internuclear distance and just have it. That's not possible. That's not possible, because gas molecules are already very far away, so you will usually not be able to bring them closer and measure it. So instead what we do is, we take two adjacent atoms, yes, belonging to two neighboring molecules of a compound, right? Yes, in the solid state of a compound, in the solid state, correct? And then what we do is, between the two adjacent atoms, okay, we will measure this distance, okay. So, 1/2 of the distance between the nuclei of two adjacent atoms belonging to two neighboring molecules of a compound in the solid state is called as van der Waals radius. Understanding, everybody? Yes? Understanding? So, this will be obviously the largest, right? This will be the largest. So, the van der Waals radius will obviously be the largest, then it will come as metallic radius, and then finally you will have covalent radius. The covalent radius are the smallest, okay. Van der Waals radius is the largest and covalent is the smallest. Great, okay. Now, what are the factors that affect the atomic radius? Atomic radius. Do you know that atomic radius is actually the biggest in the group 1 atoms? Yes, the group 1 elements have the biggest size of atomic radius, and then as you go from left to right in the periodic table, what happens is the size decreases, and then boom, again at group 18 noble gases, it increases a lot because they are noble gases, right? They don't interact with anyone. So, the number of shells is one factor that affects the atomic radius. The more number of shells are there, if you have more and more number of shells, then what will happen? The atomic radius obviously will increase, right? So, if the number of shells increases, atomic radius will increase. It is directly proportional to each other. Great, amazing. Now we go to effective nuclear charge. You know what is effective nuclear charge? Effective nuclear charge is basically the nuclear charge that an outermost electron experiences after the shielding effect. Once you have deducted the shielding effect from the nuclear charge, what is the remaining force, remaining charge that the outermost electron is experiencing? That is called as effective nuclear charge. So, in case of effective nuclear charge, with addition of proton, the nuclear charge increases, of course. If there are more number of protons and less number of electrons, the protons, the positive charges are more, so it will pull, just like Spider-Man did this and pull it closer. Now, with increase in nuclear charge, okay, if the nuclear charge increases, if the charge is a lot, then obviously it will be able to pull the electrons closer, and so the size of the atom decreases, okay, size of the atom decreases. Achha, by the way, I mistook it. With the addition of protons, if there are more number of protons, then obviously there will be more number of electrons. If there are more number of protons, then what happens? The nuclear charge increases, and if the nuclear charge increases, then obviously the size decreases. The size of the atom will decrease. That means that nuclear charge is inversely proportional to atomic radius. So, if nuclear charge increases, atomic radius decreases. If atomic radius increases, nuclear charge decreases. Got it? Yep, clear? Simple, easy. Shielding effect also affects the atomic radius. Let's check out how. So, inner shell electrons, they are shielding the outer shell electron, right? They are not allowing the nucleus to look at who is there. So, you know how we have curtains in our house? Curtains are what? Screen, correct? So, do you think that I am putting up a curtain only because it looks pretty? No, I actually also want my privacy, right? Because I want my privacy, I put the screens. I don't want somebody who is outside my house, I don't want them to see it. I don't want them to see what I am doing in the house, right? Yes, so that's the same thing. So, the inner electrons, what they do is they act like a curtain. They don't allow the nucleus to watch outside or look at the outermost electrons, and they don't allow the outermost electron to look at the nucleus, right? So, you understand this. Basically, now what happens is the attractive force of the nucleus, it does not reach the outermost electron, and because of this, the shielding effect, the atomic radii increases, because the nucleus is not able to exert its charge on the outermost electron. It remains like a free bird, and it's like I'm free, and it keeps roaming around here and there. So, basically, if shielding effect increases, atomic radius also increases. Got it? Clear? Okay. Alright. Now, let's understand multiplicity of bond. We have seen that if there is just one bond, if there is just, for example, if there is a carbon, there is a carbon, and in between them, if there is one, okay, understand it this way. See, if I am, there is a chair here, okay, there is a chair here. So, this chair, if I am holding it with just one hand, see, I can be very, very, very far away. I can be very far away, right? Yes? But if you ask me to hold on to the chair with both my hands, then I will have to come a little closer and bring my this hand also here. See, my distance increased. Check it out again. See, where was my head? Look where my head is. My head is here. My head is right at this part. Yes, this is where my head is right now when I am touching it with one hand. Correct? Now see, when I have to hold it with two hands, see, I come closer. See, I come closer. Correct? I come closer now because I have to hold it with both the hands. Right? So you see, my head is now somewhere here. Right? My head is somewhere here now. Yes. Now if you ask me to hold the chair with my leg also, then I'll have to come a little more closer. See, now I am holding it with my leg also, one leg. Now I have 3 bonds here. So now my head is somewhere here. Got my point? Very simple, very easy, right? Yes, very simple, very easy. So same like this, if I have 2 bonds, if I have 2 atoms here, and if I just have to bond them with one bond like this, then the bond length is more. The bond length is more. Okay. But then when I have to use 2 bonds, when there are 2 bonds between the atoms, now what happens? See, now what happens is, see, the bond length decreases. Okay. The bond length decreases like this. The bond length has decreased. Correct. But if there are 3 bonds, now the bond length will decrease even more. The bond length will decrease even more. Got my point? Yes. Now if you look at the table also, you can actually see the same numbers. For CC, the bond length is only 1.54. For C double bond C, it is 1.34. For C triple bond C, it is 1.20. So it keeps decreasing. Okay, it keeps decreasing. Understood? Yes. Now let's understand some of the general terms in periodic table for atomic radius. Okay. Yes. Now across a period, when you go across a period, what happens? The atomic size decreases. Z effective increases, atomic size decreases. Why? Because the number of protons are increasing. If the number of protons are increasing, that means that the effective nuclear charge increases. And if the effective nuclear charge is increasing, then the atomic size, what happens is, decreases. From left to right, atomic size decreases. Please do remember it. Okay, across a period. See, lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. Fluorine has the minimum amount of, fluorine has the minimum atomic radius. Okay. Now what happens down the group? When you go down the group, the number of shell increases and hence atomic radius increases. So from lithium, sodium, potassium, rubidium, cesium, you will see that cesium size is the largest, lithium is the smallest, cesium size is the largest. Okay. So down the group, what happens? The size increases. Alright. Moving on. Now obviously chemistry hai. It's not like there are no exceptions, there are exceptions. But you know what? A lot of people keep saying that chemistry is mystery and there is never not an exception. Actually, if you understand, I was just very recently, I was speaking with another chemistry teacher in Vedantu. And I realized that during this conversation, I realized that actually there is no exception. Basically what is happening is everybody is just following the rules. They are actually following rules. There are no exceptions, nothing at all. You just have to always remember the rules. If you remember the rules, you will figure it out. You just have to see that which rule is more applicable, that's it. So there are actually no exceptions. So if somebody is telling you now that chemistry is all about exceptions, don't believe them. Anyway, now here is a special case, okay. In group number 13, that is Bal Gangadhar Indian Tilak, that is boron, aluminium, gallium, indium and thallium, what you see is that from boron to aluminium, the atomic radii increases, no doubt about it. But from aluminium to gallium, it remains almost the same. It remains almost the same, right? Then from gallium to indium, it increases, and then again from indium to thallium, it almost remains the same once again. And do you know why? Because in case of gallium, when we come to gallium, we see that there is an introduction of 3D series. What happens? The d orbitals come into picture. And do you remember sometime back only I told you that the shielding effect of s block of the s orbitals is great, but p a little less, d even more less, f absolutely worst. It's almost as if it's not there. So because of the poor shielding effect of the 3d electrons, gallium, what happens is, understand it even more better, okay? See, s orbital is like this. So if the nucleus is here and if the electron is here, and then if I keep drawing it like this, if the electron is here for s orbital, see, because it is spherical, this electron is completely blinded by this electron, right? Getting my point? Now when we talk about p orbital shape, p orbital has a dumbbell shape. So let's say that if this is my nucleus and the electron is here, don't you think that it can see the electron? It can see the electron, right? Or if the electron, outermost electron is somewhere here, it can still somehow exert the charge, right? Now d orbital is double dumbbell. So that means there are more places from where the nucleus can actually look at the electron, right? There are more gaps from where the nucleus can see the electron and pull it. So, because of the poor shielding effect of 3d electrons, gallium as a result of effective nuclear charge, it increases, gallium what happens? It decreases the size. The effective nuclear charge increases, gallium's size decreases. Got it? Yeah? Alright guys, moving on. Now there are some more special cases, okay? In the transition series, in the first transition series, you will see that the covalent radii of the elements, they decrease from left to right. Left to right, it decreases, okay? Yes, alright, across a row. Until near the end, when the size just increases slightly. Why? Because the screening effect is same as the nuclear charge. The amount of screening effect is happening that is almost equal to the nuclear charge, and that is why they all nearly have the same size, okay? They almost have the same size. But now as you go beyond, you see that the screening effect increases, but the nuclear charge remains same. Screening effect increases more than the nuclear charge. So the nuclear charge is still almost remaining the same, but the screening effect has increased more. So what happens here, you see a huge difference in the atomic radius, okay? But here you see the atomic radius is still more, okay? Because it decreases. Why? Because there is a constant increase in the nuclear charge. There is an increase in the nuclear charge, increase in the nuclear charge, increase in the nuclear charge, and bam! Screening effect and nuclear charge almost remains the same, okay? Screening effect and nuclear charge almost remains the same, and then in copper and zinc again it increases. Got it? Okay. So let's talk about which has the maximum atomic radius. Is it aluminium? Is it silicon? Is it phosphorus? Or is it magnesium? Guys, just remember that aluminium, silicon and phosphorus, they are all in the p block. Whereas magnesium is a group 2 element, so obviously it has to be magnesium. Like I said, from left to right when you go in the period, the atomic radius decreases. So the left side elements have higher atomic radius or larger atomic radius, okay? Alright, moving on. Now we come to ionic radius. Ionic radius is going to be easy, everybody. So ions, what are ions? Ions are basically atoms which have a charge, right? Yes, ions are formed either when you gain an electron, either when an atom gains an electron, or when they lose an electron, right? Yes. So on the basis of this, the ions can be classified in two types. Yes, ions can be classified in two types. One is cation. The cations are positively charged ions. And there are anions. Anions are the negatively charged ions where you have gained an electron. When you gain an electron is when you have negative charge, and when you have lost an electron is when you have positive charge, right? Understanding, everybody? Getting my point? Yes. So for example, okay, let's understand it this way. I have a very good example, okay? You know, we all belong to the middle class, right? We all belong to the middle class, this thing. Now when we lose some money, we go poor, right? We go poor, isn't it? Yeah. But when Ambani loses some money, he becomes richer. Do you know how? Because he invested in somewhere from where he will get more money. So when Ambani loses some money, he becomes positive. He is like, whoo, I'm going to get some more money. He thinks, he already knows that I'm going to be, 10x richer than this once I have lost some money. So he is positive, right? Yes. Now what happens is, but if I have gained, when you have gained, what happens? You get more negative charges, okay? You get more negative charges. Understand it this way, everybody. So if there is an atom, in the atom, if there are, let's say 10 protons and there are 10 electrons in the initial, to maintain the neutral, right? This is a neutral atom, right? Now from here, if I take away one electron, then that means that there are 10 positive charges and there are 9 negative charges. 9 negative charges. Which one is more? The positive charges are more. So the atom will show you a positive charge. That means that this is a cation. This is a cation. Alright. Now if I have 10 positive charges, I give one electron and I have 11 negative charges. Now what is this? This will become an anion, because this will start showing you its true negative colors. Got it? Yeah. So this is cation and anion. Now anionic radius, you have to understand that because the number of protons are lesser than the number of electrons. So what happens? The number of protons are lesser than the number of electrons. You have more number of electrons, and those more number of electrons are not tolerated by the protons. You know, the protons are not enough to tolerate the number of electrons basically. So what happens is they fly away. They're like, we are free birds, I'm going to move, I'm going to go here, you cannot do anything. And that's how what happens is the anions, they are bigger in size, okay? The negative charged anions are bigger in size. Got it? Now we go to cations. Now cations have what? They have more number of protons but less number of electrons. So because they have more number of protons, the Z effective, the effective nuclear charge is more, and they can bring all the electrons closer, and that's why the cations are smaller in size. Got it? Now tell me, ionic radii of titanium 4 plus, manganese 7 plus. Okay. Now titanium has an atomic number of scandium, titanium 21, 22. Okay. So 22 means 3d24s2. As you go by, you will learn it. Don't worry. Okay. All the electronic configuration, atomic number, you will learn it. So 3d24s2. Yes. And then manganese. Manganese is 25. Yes. So 25, that means 3d54s2. Okay. Alright. Now what will happen is, in this case, this will also go, this will also go. This will also go, this will also go. 4 plus, right? Yes. But 7 plus, no, it is wrong. This will also go, this will also go. 7 electrons less. Here, 7 electrons less. Here, 4 electrons less. Which one will be bigger? This will be bigger. So this is wrong. 35 Cl minus, 37 Cl minus. Both of them have 1 minus charges. If they're just talking about isotopes, doesn't matter. Wrong. K plus is greater than Cl minus. Makes sense, right? Yes. Makes sense, isn't it? This one is a positive charge, this one is a negative charge. Does this make sense to you? Does this make sense to you? No guys, it doesn't. K plus, right? Plus it is. Plus means it has 1 electron less. If it has 1 electron less, that means the size has to be smaller. So this is also wrong. P3 plus is greater than P5 plus. This makes sense. Yes. If 3 electrons you have lost, then definitely your size will be bigger than 5 electrons. If you have lost 5 electrons, obviously your size will be smaller. Right? Got it? Yes? Okay. Now we come to isoelectronic species. Isoelectronic species, we had introduced this topic in structure of atom, if you remember, when we read all about iso, remember isotopes, isobars, isotones, isodiaphers, isoesters, isoelectronic species, paramagnetic, diamagnetic, all of this we have, we introduce it. So what are isoelectronic species? Basically the species that contain the same number of electrons, but they differ in the magnitude of their nuclear charge. So the nuclear charge is different, but they have the same number of electrons, my dear students. See, if you see N3 minus, okay, nitrogen has 7 electrons, has 7 protons also, right? If you give it 3 more electrons, then what happens? The number of electrons are 10. For O2 minus 10, yes, F minus 10, neon 10, Na plus 10, Mg2 plus 10, Al3 plus 10. Now what is happening? The nuclear charge and the force of attraction is increasing, but the ionic radius is what is happening? It decreases. This will have the smallest ionic radius because there is the Z effective charge is plus 13. There are 13 protons who can pull those 10 electrons, so obviously the ion is going to be of smaller size, right? Let's do this, guys. Let's do this. So the correct order of the ionic radii is, let me give you a very simple tip, very simple tips. Yeah, very simple tip. O2 minus, N3 minus, F minus, Mg2 plus, Na plus and Al3 plus. Always write the one that has the biggest charge, that will be the smallest. So Al3 plus. Yes, then you write Mg2 plus, very simple, very easy. Then you write Na plus, very simple, very easy. Then you write F minus, then you write O2 minus, and then finally write N3 minus. This is your answer. That means that I think it is option number C. Yes, it is option number C. See, that's all you had to do. Okay, that's all you had to do. Got it? Great. Moving on. Chloride ion and potassium ion are isoelectronic. Then, if chloride ion and potassium ion are isoelectronic, then what will happen? Potassium ion is relatively bigger, depends on the other cation and anion. Their sizes are same. Chloride ion is bigger than the potassium ion. Chloride ion and potassium ion are isoelectronic. Okay, so potassium will have to, let's say that chlorine and potassium, right? So what will happen is, chlorine is that side, potassium is here. So chlorine will have to lose some, potassium will have to gain some to be equivalent, right? So chlorine atom will be smaller, yes. Potassium ion is relatively bigger. I think that it is option A only. Oh, this is your homework question. Oh, sorry. This is your homework question. You do it. I'm not going to do it. This is your homework question. You do it. Okay. Anyway, I was about to solve it. Thank God I did not solve it. Anyway, now we come to ionization energy. What is ionization energy? Okay. Very simple, very easy, guys. I always give this example, but let me give you this example one more time. Okay. Basically, what happens is ionization energy. So I really love shopping, right? I'm a woman. Come on. I'm a woman and I really love shopping. And even now, believe it or not, I promise I actually have a 8,000 rupees Myntra card that is ready. I have it. I swear to God I have it, right? I want to buy those. But now the moment I click on place order, what will happen? From my bank account, 8,000 rupees will go, but I will get that minute amount of happiness, right? That, oh, my new clothes are coming. What did I do? I lost some amount of money to gain those clothes for me, right? What did I do? I lost some amount of money to gain those clothes for me. And basically, that's exactly what happens in ionization energy. So when you want to take away an electron from an atom, right? So what was happening? Myntra was taking away some amount of money from me, and in return, to make me happy, it had to give me those clothes. Like, Auntie, you take your mangoes, Zara, Veromoda, everything. You take it, right? That's what Myntra did, correct? So the very same way, when I want to take an electron from the atom, what I actually do is, I also have to give the atom some amount of energy. That, Papa, atom, don't shout and all, yeah, you be fine, okay? Don't shout and all, it's okay, don't worry. Nothing will happen, I'm just taking one electron, see, I'm giving you energy. When I give it energy, only then I can take that electron. So ionization energy is the amount of energy given to the atom to take away one electron from an isolated gaseous atom. Basically, you had something in solid. Let's say the atom was in the solid form. So from solid, I have taken it to the liquid form. From the liquid form, I have taken it to gaseous form. And then I have separated the atom. And now I want to take an electron from the atom. So I have to give it some energy, right? That, my dear student, is called as your ionization energy. So ionization energy, basically when you give an ionization, when you give some amount of ionization energy, it usually forms a cation. What does it form? It forms a cation. Got it? Yes. Now, do you know that there are different ionization energies? There is ionization energy 1, there is ionization energy 2, and there is ionization energy 3. Now, the first ionization energy is usually less, the second ionization energy is a little more, and the third ionization energy is even more, right? Understand it this way. I have given this example any which ways, but I am going to give it to you again. So, let's just say that one fine day you are all spamming in the chat and I become very angry. I am like, "Argh!" But then now what happens is, everyday students come, ma'am, don't be angry, okay? Ma'am, don't be angry, okay? And now that I was angry, I know my fault. I'm like, yeah, I actually shouldn't be angry on my kids. They are the students. They are kids. I shouldn't be angry at them, right? I shouldn't be cross with them. So what will I do? The second time, it's going to be really hard for you to make me angry. Now, second time, by mistake, I am angry. The third time is going to be even more tougher for you to make me angry, right? So, the atom also understands that, hey, this is my fault. I gave away one electron. I am not going to give any more electron. So, it gave one electron. The second time is very careful. Like, this is my atom. This is my electron. Not going to give it. Now, second time also, somehow you have given it lot of energy, like, Papa, don't cry and all, yeah, I'll give you some more energy, it's okay, just give it to me. Second time also, if you have taken it, third time it's like, not giving you anything. It will try to protect its electrons even more, understanding? But although sometimes it does, you know, there are certain differences also, you will see. You will see those exceptions as well. So, this is basically what I am saying, that ionization energy 1 is lesser than 2 and then it is lesser than 3. 3 is usually the highest, and as you go on and on, it becomes harder and harder for you to take out the electrons, because the atom becomes very possessive at that time, that no way, I am not giving you my electrons, right? The atom becomes very, very, very possessive. Got it? Okay, all right, now moving on from here, so let's understand that how atomic size can affect the ionization energy, okay? So, if you have greater atomic size, you know that the effective nuclear charge is not even able to reach the last electron, right? So, what will happen? Ionization energy will be less, because if I am the nucleus and let's say that there something is there, I am not even able to hold it. So, what will happen? Somebody else will be like, I am taking it away. Gone. So, you can give less amount of energy and you can still take away the electron. So, basically what I mean to say is, atomic size is inversely proportional to ionization energy. You increase the atomic size, ionization energy decreases. Yeah, and vice versa. Got it? Clear. Now we come to nuclear charge, okay. So, nuclear charge is directly proportional to ionization energy. As you increase the nuclear charge, as you increase the effective nuclear charge, the ionization energy also increases. Why? Because as you increase the nuclear charge, the number of protons that are there, they are easily able to hold on to the electrons and they are not letting you go. They are not letting go of the electrons. So, ionization energy increases. You have to give more energy to the atom to take away the electron. Clear? Crystal clear? Easy peasy biryani tasty? Awesome. Next. This is comparatively easy. It's just that there are too many things that you have to remember. Then comes screening effect. What happens with screening effect? If screening effect increases, ionization energy decreases, because the more the inner orbital electrons are able to shield the outermost electrons, the nucleus will not be able to see the electron. So, you can easily take away that electron. You can just give it less amount of energy and you can take away the electron. Got it? Yeah, great. Now we come to electronic configuration. Now what we have seen is the half filled or the fully filled, that is P3, P6, D5, D10. These ones are extra stable, you know, they are very stable and they don't want to give their electrons away. Why? Because their stability will get messed up, yeah, right? So, they don't want to give out their electron, okay? Which is why at that point of time what happens? With this stability, the ionization energy increases. So, it's very hard to break this stability. Yes. So for fully filled and half filled, what happens is the ionization energy increases. Got it? Okay. Now, when you move from left to right in the period, the ionization energy usually increases because Z effect also increases. That means the effective nuclear charge also increases. When you move from top to bottom, what happens is the ionization energy decreases because the atomic radius increases. Now obviously there are some special cases, right? For transition elements especially, generally in period the ionization energy increases, right? But the increase is not so regular. When you come to that 3D series, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, right? What happens is you see that the ionization energy, the regularity is not there. It's very abrupt. Like it increases sometimes, it decreases sometimes, it increases sometimes, it decreases sometimes. That is because, understand this, differ only very slightly from each other, right? And for iron, cobalt, nickel, copper, the values are very close to each other. From copper and zinc, from copper to zinc, it again increases, but it is very close, okay? Now, why is that so? Why is that so? Now, when I said ionization energy, do you remember that I spoke about isolation of gas? Isolation of gas. So, understand this, my dear student. Please try, okay? Very, very important, okay? So, what is happening is basically I have a solid metal. From this solid metal, I have to take it to isolated gaseous state, right? Do you think that it is that simple and that easy? Is it that simple, that easy? No. First, I have to melt it. I have to take it to liquid state. I had to give it some heat. Yes. Now, from the liquid state, I again have to heat it and I have to take it to now gaseous state, right? Now, once I have taken it to gaseous state, now I also have to isolate it, right? I also have to isolate it, right? Yes. So, in case of these 3D elements, right, this scandium, titanium, vanadium, chromium, manganese, iron, cobalt, copper, nickel and all of that, what happens is that from solid to liquid when it gets converted to solid to liquid, here is something called as hydration enthalpy as well that is working, okay. There is something called as hydration enthalpy as well, right. So, in case of this 3D series, nothing is irregular actually. Nothing is regular actually. Their hydration enthalpy is not regular. Their ionization enthalpy is not regular. Their sublimation energy is not regular. Which is why what happens is you get to see these irregular trends in these 3D series. Okay. In this 3D series, what happens is you get to see this irregular trends. Are you understanding? So, I am going to just remove it because this was just an example that I told you. Okay. Alright, got it? Clear. Basically, this is the graph that you get to see here. Okay, this is the graph that you see. Alright, as you can see, from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. See how it is increasing. Yes, it's increasing, right? Even in case of noble gas, it's very hard for you to take away, right? You cannot. And then again here what they are showing is as the size increases, see lithium, sodium, potassium, rubidium and cesium. As you go to cesium, there is a steady drop in the ionization energy because atomic number increases. Okay. Alright. Now check it out guys. Now check it out. Yes. Ionization energy, it increases across the period. That's what we said. But when we go to beryllium and boron, beryllium is in group 2. Boron is in group 13. However, we see that beryllium has more ionization energy than boron. Why is that so? Why is that so? Okay, let's check it out. Beryllium and boron, right? Beryllium and boron. Okay. So, what is beryllium's atomic number? Beryllium has an atomic number of 4, right? And boron has an atomic number of 5. So, for beryllium, it is 1s2 and 2s2 fully filled. Do you see? Fully filled. Now, check it out here. 1s2, 2s2 and then 2p1. There is just one electron. Don't you think that it can easily give away that one electron and attain the fully filled stable state? It can, which is why it easily gives away this electron. That is why the ionization energy is so less, and you can see that beryllium has a higher ionization energy. That's because it has a fully filled stability. Same with nitrogen and oxygen also, my dear student. Nitrogen has what? 7. Oxygen has 8, right? So for nitrogen, if I write it 1s2, 2s2 and 2p, 2, 2, 4, 2p, 3, 3, half filled, half filled. Now check it. 1s2, 2s2, 2p4, 4, 4, 8, 4. It can readily give away 1 electron to attain the half filled stability. That's why oxygen has less ionization energy. Same with magnesium and aluminium as well. Okay, same with magnesium and aluminium as well. Find out their atomic number and do this on your own and figure it out that why aluminium has lesser ionization energy than magnesium. Okay. Now we come to something called as electron gain enthalpy. What is electron gain enthalpy? Okay. So I just told you that if I want to take away, okay, if I want to buy some clothes from Myntra, then I will have to spend some money. But what if I want to sell my clothes? If I want to sell my clothes, then I will get money, no? Because I am giving away something. I am giving away that happiness that I get from buying new clothes. When I buy new clothes, I get certain amount of happiness. Now that I am selling my clothes, I am losing out on that happiness. Right? What do I need? I need to be happy again. I need some money. Isn't it? The same thing happens. So when you try to push an electron towards an atom, so the atom was neutral, the atom was absolutely fine, the atom was not asking for it, right? So what happened was, this was an atom, now you are trying to push an electron towards it. So when you do this, when you push an electron in the atom, do you know what happens? The atom releases energy. The atom says that, you're anyway pushing an electron, I don't need so much energy, take it away and go. So energy that is released when an electron is added to the valence shell of an isolated gaseous atom is called as electron affinity or electron gain enthalpy. Actually not electron affinity, this is wrong. This has to be electron gain enthalpy, okay. This is what? Electron gain enthalpy. Got it? Alright, yes. Now what are the factors that affect electron gain enthalpy? Same as it is, effective nuclear charge. The more is the effective nuclear charge, the more the electrons are closer towards the proton, it will be easier for you to push an electron, because the moment you push the electron, the proton is like, yes, yes, amazing, 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 I already have positive charge, bring it on, it will take it out, it will take it, right. So as the effective nuclear charge increases, what happens? The electron affinity, or that is the electron gain enthalpy also the electron gain enthalpy also decreases. What is electron affinity? Electron affinity is basically how much willing I am to take that electron. The love for electron, affinity, I have certain soft corner for the electron, I want to take that electron. So how much is it that I am willing to take that electron is electron affinity, love towards the electron. Got it? Okay. Alright, great. Now we come to atomic radius. So higher is the atomic radius, lesser is the effective nuclear charge and lesser is the electron affinity. As the effective nuclear charge reduces, the atom does not want an electron. The atom is like, hey, I'm already having problem, taking care of. Understand this. If in a class I have 25,000 students, do you think that I'll be able to take care of each of them? Not possible. But if I have 40, I don't mind, right? I'll be like, you can send another kid. I'm already attending to 40 students. I can have 41 students, no problem. But if it's 25,000 students, and if somebody says that, madam, can we send another one? I'll be like, you crazy? I'm already suffering so much. I'm getting stress and everything. You want to send another student? Not going to happen. So electron affinity is inversely proportional to atomic radius. Got it? Clear? Awesome. Now we go to factors affecting electron gain enthalpy. Okay, the screening effect. Once again, we are doing electron gain enthalpy. Sorry. I see the heading and I'm like, whoa, new thing. Screening effect. Okay, what about screening effect? As the screening effect or the shielding effect increases, what will happen? The electron affinity will also decrease. Now what is happening? See, you need the positive charge, you need the proton to attract the electron and bring it in, right? But now the protons are not even able to see the electrons, it's not even able to see those outermost electrons, right? So what will it do? It will be like Jane Vidoya, what am I, Poda, right? Yes, it will be like Poda, I don't care. I am already not able to, tolerate those which are at the valence shell. The electrons that are at the last shell, I am not even able to see them, I am not even able to control them. How will I control another one? So they are saying, Poda, take it and go, I don't care. Alright. Then I spoke to you about half filled and fully filled electronic configuration. So once again, the half filled and the fully filled electronic configuration, they are very stable and they do not have the tendency to accept an extra electron. They don't. They just don't want it, right? So now what happens across a period? Across a period, with the increase in atomic number, what happens is the delta electron gain enthalpy becomes more negative. It becomes more negative. What do we mean by that? Because across a period, the Z effective increases. If the effective nuclear charge increases, that means the electron has the capacity to take in more electrons, right? So what happens? It becomes negative. That means that the electron affinity is increasing, right? And it will be easier to add an electron to a small atom, right? Do you think that? Do you think that? It will be easier. That's what we say in theoretically we say that it will be easier to add an electron to small atom, but actually that's not the case, okay? Fluorine, if you look at fluorine, you will see that fluorine does not want to take an electron. Really, like fluorine just does not want to take an electron, okay? Alright, and then when you go from left to right, what happens? The electron, like I just said, that effective nuclear charge increases. So what happens? Electron gain enthalpy also decreases. But down the group, what happens, guys? Down the group, what happens is with a group from top to bottom, it becomes less negative. Why? Less negative. Why? Achha, by the way, understand this, because the energy is released, so there is a negative sign. If energy was absorbed, then it was a positive charge, okay? You would have had added a positive sign, okay? But here, because it is releasing, so we add a negative sign over it, okay? So here what is happening is, within a group from top to bottom, delta Eg, that is electron gain enthalpy, it becomes less negative because the atomic sizes increases. And now when you want to add an electron, it would be a larger distance from the nucleus. The nucleus is not even able to control all the shells that it has, right? So it becomes a little tough. Got it? Now we come to electron negativity. So do you see how there is a tug of war that is going on? There is a tug of war that is going on. Yeah? Like, no, I want to do it. No, I want to do it. I want to do it. No, I want to do it. That's exactly what is electronegativity. That's exactly what is electronegativity. Basically, the ability of an atom. Yes? So take a look at it. Basically, what happens is, let's say that there are two atoms here, okay? There is one atom here, there is one atom here. And both of them are actually sharing this electron. They are both sharing this electron, this pair of electron, right? Now, this one will also pull the paired electron towards this side. This one will also pull the shared electron this side. Now, whoever can pull it closer, they are more electronegative. They are more electronegative. So, unlike all the other properties, we were talking about isolated atom, this time we are talking about a shared pair. And this time we are talking about something that is already in a bonded state. Are you understanding? That means there are two atoms that are together, they bonded together, okay? And then one of them pulls the shared pair of electrons towards them and they become the more electronegative one. Got it? Yeah? Okay. So there is a scale called Mulliken scale. What is this Mulliken scale? Mulliken gave the electronegativity as the average value of ionization potential and electron gain enthalpy. So Mulliken said that if you add the ionization potential, ionization energy, ionization enthalpy, whatever you say, same thing absolutely. So ionization potential and electron gain enthalpy, when you add them and when you divide them by 2, that is your Mulliken scale. That's how Mulliken gave the electronegativity. Okay, but that was not the right one. After Mulliken, there was also Pauling scale. Now Pauling said that the electronegativity difference between the two atoms, you can give it as XA minus XB is equal to, there is a number 0.208 root over delta. What is delta? Delta is the bond enthalpy, the bond energy of A and B when they are forming a bond, the bond energy of AA of same type of atom and the bond energy of BB same type of atom. Okay. So if there is let's say that there is carbon and there is oxygen. Okay, there is carbon and there is oxygen. So when I'm trying to find the delta, what I'll do is bond enthalpy of carbon and oxygen minus root over bond enthalpy of carbon and carbon multiplied with bond enthalpy of oxygen and oxygen. That will give me the result. Okay, that will give me the result. Understood? So what are the factors that affect electronegativity? Atomic size is directly proportional to electronegativity. Effective nuclear charge is directly proportional to electronegativity. Hybridization state of an atom. What is hybridization? You know, right? What is hybridization? When the orbitals, they mix together, they come together and they try to have the same energy level, that is your hybridization. You know what is hybrid, right? What do? Don't we do this like cut the rose plant, cut the hibiscus plant, mix them and together you have what? China rose. Just kidding around. So when you're mixing and matching, and that's why how you create hybrid, right? So here also orbitals are getting hybrid. So S is a different orbit, P is a different orbital, but when you bring them together, they have different energies, right? When you bring them together, they are like, let's match our energies. And they form a bond. So that is called as hybridization. So you see that the percentage S character in any hybridization like SP, SP2, SP3, what is the amount of S character that is present? That also dictates the electronegativity. Okay. So if there is S and P, then 50% S character. So 50% will be S, 50% will be P, right? 50% S, 50% P. Together they are hybridizing, right? So 50% S, 50% P, together they are hybridizing, the electronegativity becomes 3.25. But if I have SP2, then S will be 1/3 of 100, P will be 1/3, another P will be 1/3, together they will become 100, right? So that comes up to 33%. So this time electronegativity reduces to 2.75. Now if I have SP3, S 1/4, P 1/4, another P 1/4, another P 1/4, together they will become 100%. So 25, 25, 25, 25 together they become 100%. So 25% is your SP3, S character is 25, so the electronegativity becomes 2.5. And finally the oxidation state. Okay, how does oxidation state affect it? The electronegativity value increases as the oxidation state, that is the number of positive charge of the atom increases. If the number of positive charge increases, then the electronegativity value increases, because then they can pull the electrons closer, obviously, because it already has lesser number of electrons, it has more number of positive charge, it can easily pull the electrons closer. Got it? Easy peasy. Now what is the trend of electronegativity? It increases when you go from left to right. Yes. When you come top to bottom, it decreases. Top to bottom, it decreases. And then finally, application of electronegativity, metallic and non-metallic nature. So on moving from left to right in a period, the electronegativity of the element increases. And that means that the metallic character decreases. So if electronegativity increases, metallic character decreases. On moving down a group, again the electronegativity of the element decreases. So what happens? Metallic character increases. It's vice versa. Electronegativity increases, metallic character decreases. Electronegativity increases, then what happens? Electronegativity decreases, then metallic character increases. Got it? Yes. Then we talk about bond strength. So if the electronegativity difference of covalently bonded atoms increases, the bond energy of the covalent bond also increases. For example, the order of the HX bond strength. Yes, HX, see, HF is highest because this is highly electronegative. Then comes HCl, then comes bromine, and then comes iodine. So what happens is electronegativity difference of covalently bonded atoms, that is delta X. If the electronegativity that increases, then the bond energy of the covalent bond also increases. And that's why you see that HF has the highest electronegativity. Okay. Alright, I hope you understood. Finally, we come to partial ionic character in covalent bond. So a lot of time we thought that if it is covalent, then it has to be completely covalent. That's not the case. There is actually something called as partial ionic character in covalent bond. So what is it? So there was this two guys called Haney and Smith, and they said that ionic percentage is equal to 16. See, Xa minus Xb, this is again electronegativity, plus 3.5 Xa minus Xb, and now you square it. So what is Xa? X is the electronegativity of A. So when you're subtracting, that is basically your electronegative difference, and here you are squaring the electronegativity difference. Okay. Now if Xa minus Xb, if it is greater than or equal to 2.1, then the ionic percent here is greater than 50%. That means it is an ionic bond. This comes in the exam, guys. This is important. This comes in the exam, right? But if the difference is less than or equal to 21, then that means that the ionic percentage is less than 50%. And that means we say that it is more inclined towards the covalent bond. Okay, it's more inclined towards the covalent bond. Alright. We can also talk about the acidic and the basic nature of oxides. Let's just consider an oxide called AO. So there is A and there is O. This is the electronegativity of A, electronegativity of O. If it is greater than 2.3, basic oxide. If it is equal to 2.3, amphoteric oxide. If it is less than 2.3, acetic oxides. That's it, done and dusted. You can actually calculate it. And with this note, we have come to the end of the session. By the way, there are some more tips and tricks for which I will be recording another video. But however, the chapter is complete. But related to JEE, I am actually going to do a separate session where I am only going to give you all tips and tricks about how to find out the group, how to find out the electronic configuration, and all of that I will tell you in just half an hour. So don't forget to watch that session, and thank you so much for watching this session. I will see you very, very soon. Tata, bye-bye, and lots of love.